What if I told you that finding every missing interval between two bounds is just a matter of placing two virtual sentinels at the ends and scanning once? We are given a sorted array of distinct integers, plus a lower and an upper bound. Our task is to list all the inclusive ranges that are not present in the array but fall between lower and upper. For example, with the array 0, 1, 3, 50, 75, and bounds 0 and 99, the missing ranges are 2, 2, 4, 49, 51, 74, and 76, 99. Each missing interval must be reported as a pair of start and end values. A naive approach would be to generate every integer from lower to upper, store them in a list, then remove each element that appears in the input array, finally compress the remaining numbers back into intervals. This touches every number in the full range, so its time grows with the size of the interval, not the size of the input array. In big O terms, that means O, upper minus lower plus 1, time, and O, upper minus lower plus 1, extra space, which quickly becomes impractical when the bounds are large. The key insight is to treat the lower bound minus 1 and the upper bound plus 1 as artificial previous and next numbers. Then look at the gap between each consecutive pair. First, we initialize a variable called previous to 1 less than lower. Then we iterate from index 0 through the length of the array, using the current value as either the next array element or, when we have exhausted the array, upper plus 1. For each step, we compute the difference between current and previous. If that difference is at least 2, we have a missing interval. The start of the interval is previous plus 1. The end is current minus 1. If start equals end, we add a single element range. Otherwise, we add the full interval. After handling the gap, we move previous forward to the current value and continue. This loop runs exactly once over the input array and handles the edges automatically because of the sentinel values. Let's walk through the example. We start with previous set to minus 1 because lower is 0. First iteration, current becomes the first array element, 0. The gap between 0 and minus 1 is only 1, so no missing range. We move previous to 0. Next, current is 1. Gap is still 1, no range. Move previous to 1. Then current is 3. The difference is 2, so we have a missing interval from previous plus 1, 2, to current minus 1, 2. We record 2, 2. Update previous to 3. Next current is 50. Difference is 47. So missing start is 4. End is 49. Record 4, 49. Set previous to 50. Current becomes 75. Gap gives start 51. End 74. Record 51, 74. Update previous to 75. Finally, we reach the end of the array. So current is upper plus 1, which is 100. The gap is 25, giving start 76 and 99. Record 76, 99. The loop ends, and we have exactly the 4 intervals we expected. You'll recognize this pattern whenever a problem asks for missing or extra intervals within a numeric range. Just add virtual boundaries and scan for gaps. The algorithm runs in linear time, big O of n, where n is the length of the input array. It uses big O of n space to store the resulting intervals, plus a constant amount of extra variables. Give this sentinel trick a try on similar range problems, and check out the next video where we apply the same idea to merging intervals. If you found this useful, hit like, subscribe, and ring the bell for more algorithm insights.